Welcome back, everyone, for another deep dive. Today, we're going to be tackling some of the biggest mysteries in physics, those questions that have kept scientists up at night for, well, probably centuries. But the exciting part is we're not just going to list out the problems. We're diving deep into some potential solutions, some really out there ideas that might just change the way we think about the universe.
Yeah, the material you've given me is pretty mind-blowing, to be honest. It covers a huge range of topics. We're talking about the very fabric of reality, space-time, quantum gravity, those big ones. Then we've got dark matter, dark energy, the stuff we can't see but know is out there. And even things on a much smaller scale, like questions about the neutron's lifetime, how superconductivity works. It's a lot to unpack.
It is. But there seems to be a common thread running through a lot of these sources, right?
Yes.
This focus on information density coherence energy and something called the distributing force theory. Seems like these ideas are being used to tackle all sorts of problems, and that's what we're going to explore.
Absolutely. It's like these sources are saying, hey, what if we look at all these mysteries through the lens of information, coherence, and energy? And when you do that, some pretty wild solutions start to emerge.
So our mission for this deep dive is pretty clear. We need to get to the core of these proposed solutions. What exactly do these terms, coherence, energy density, information, balance, what do they actually mean? And maybe more importantly, what are the implications of these ideas for our understanding of, well, everything?
Right, because if these ideas are right, then we might have to seriously rethink some of our most basic assumptions about physics and the universe. So maybe a good place to start is with that biggie, the search for a theory of everything, or TOE. It's been the holy grail of physics for decades, trying to bring together quantum mechanics, which describes the world of tiny particles, and general relativity, which explains gravity and the large-scale structure of the universe.
And as far as we know, those two just don't play nice, right? They're like two different languages trying to describe the same reality.
Exactly. Quantum mechanics is all about probabilities and discrete energy packets, while general relativity describes smooth, continuous space-time. They just don't seem to fit.
So how do these new perspectives, the ones we're focusing on today, try to bridge that gap? How do they approach this quantum gravity problem?
Well, the theory of information density coherence energy, that one's a mouthful. It's just a really radical idea. Maybe space-time itself isn't fundamental. Instead, it might emerge from something even deeper, the coherence of these underlying infer-energy fields.
Okay, I'm going to need a little help picturing that. What are infer-energy fields?
Think of it like a vast network, but instead of physical connections, it's made up of information and energy. And when these points in the network sync up, when they become coherent, that's what gives rise to space-time as we experience it.
So it's not that particles exist in space-time. It's more like space-time is created by the relationships between these information and energy points.
Yeah, something like that. And this has some huge implications. For example, gravity, which we usually think of as a force caused by a particle. The graviton might actually be something totally different. It could be a manifestation of quantum entanglement, that spooky action at a distance, but on a cosmic scale.
Whoa, so gravity isn't a force, but an emergent property of this interconnected web of information and energy. That's wild. And what does that mean for all the laws of physics we've worked so hard to discover?
Well, it could mean that our current laws are more like approximations rules of thumb that work really well in the everyday world but break down at the most fundamental level. Maybe the true underlying laws are based on information theory, on how information is organized and processed in the universe.
So it's like the universe is a giant computer, and what we perceive as reality is just the output of that computation. Okay, I'm starting to get a headache, but in a good way.
Now, we mentioned another approach, the distributing force theory. How does that one tackle quantum gravity? Well, it suggests that all forces, including gravity, emerge from something called gradients in a fundamental coherence field. Basically, imagine this field of pure coherence. It's like the most organized, harmonious thing you can think of. And whenever there's a change, a difference in this coherence, that creates a force.
So a force is like a wrinkle in this perfect coherence field.
Exactly. And gravity, being the weakest force, would be the most broadly distributed wrinkle, if you will. Now, here's where it gets really interesting. The distributing force theory also says that space-time itself arises from quantum informational interactions. It's like at the most fundamental level, it's all about information exchanging and interacting, and from that, space-time emerges, and gravity is just a byproduct.
So both of these approaches, even though they come at it from different angles, they both seem to be saying that information is the key, that it's more fundamental than space-time or the forces we observe.
Exactly. And if that's true, It really opens up a whole new way of looking at things.
Okay, so let's see how these ideas apply to some other mysteries. One that's always bothered me is the whole thing with dimensionless physical constants. These are those pure numbers, like the fine structure constant, that pop up in our equations, but we don't really know why they have the values they do. It's like the universe is finely tuned and it's kind of creepy.
I know, right? It's like someone dialed in those numbers just right to make our universe possible. But the sources we're looking at today, they have some pretty radical suggestions. They say that maybe those constants aren't arbitrary at all, but they emerge from deeper principles of information coherence and energy information balance.
So it's not some fine tuning. It's more like those values are the only ones that make sense in a universe built on information and coherence.
Yeah, that's the idea. And some even suggest that even the dimensional constants, like the speed of light or Planck's constant, might not be truly fundamental either. They might emerge from these deeper information-based principles.
Okay, now my head really hurts. So the very foundations of physics, the constants we thought were unchangeable, might actually be emergent properties of information.
That's what these sources are suggesting. Now, the distributing force theory also chimes in on this whole thing with constants. It agrees that information coherence is at the root of it all, but it goes a step further.
Okay, how so? What else does it say?
It says that there might be a set of fundamental ratios that determine all the physical constants we see. And it makes a really wild prediction about the fine structure constant, the one that determines the strength of the electromagnetic force.
Oh, that's a big one. So what's the prediction?
It says that the fine structure constant might actually vary a tiny bit, depending on the strength of this distributing force.
A varying fine structure constant. That would be huge. Like, wouldn't that mess with everything from atoms to the way light interacts with matter?
Totally. But the changes would be super subtle, only noticeable in environments where coherence is really, really high. Like, imagine being able to create a region of ultra-high coherence in a lab. We might be able to actually measure those tiny shifts in the fine structure constant.
That would be amazing. Okay, so we're seeing this theme of information and coherence popping up everywhere, from space-time to the constants of nature. Let's move on to something even weirder: black holes. We know there are these regions of intense gravity where nothing, not even light, can escape. But what happens to all the information about the stuff that falls in? Does it just disappear?
That's the infamous black hole information paradox, and it's a major headache for physicists. Because if information is truly lost in a black hole, then it violates some of our most cherished laws of physics.
Right. Quantum mechanics says information can't just vanish. So how do we resolve this?
Well, one potential solution is this idea called the holographic principle. It's kind of hard to wrap your head around, but the basic idea is that all the information inside a three-dimensional volume of space, like a black hole, can be encoded on its two-dimensional surface. Like, imagine a hologram. You have a flat image, but it contains all the information to create a three-dimensional image.
So it's like the information is preserved on the event horizon, the boundary of the black hole, even if we can't access it from the outside. Okay, that's pretty trippy. But what about those two theories we're focusing on? What do they have to say about black holes and information?
Well, the distributing force theory has a really interesting take on this. It says that black holes aren't actually singularities, points of infinite density. Instead, they're what it calls coherence condensates, regions where information density hits this critical threshold, like it's been squeezed as far as it can go.
So what happens to the information then? Does it just get stuck there?
Not necessarily. The theory suggests that instead of being destroyed, the information is forced into this process of redistribution. Like, imagine you're stuffing a suitcase at some point, you can't cram any more in, and you have to reorganize everything.
Okay, so black holes are like cosmic suitcases that are constantly being repacked.
Yeah, something like that. And the information doesn't just sit there. It might get transformed into this energy coherence field that surrounds the black hole. And the black hole itself could act as a sort of information processor, potentially even emitting structured data back into the universe.
So instead of being information destroyers, black holes might be more like cosmic libraries or even giant quantum computers. That's a huge change in perspective. Okay, let's zoom out now and talk about the very early universe. We've got these puzzles like cosmic inflation and the horizon problem things that suggest the universe went through this crazy rapid expansion right after the Big Bang.
Right. The horizon problem is especially weird. It basically says that different parts of the early universe, regions that should never have been in contact with each other, are somehow incredibly similar. And inflation, this period of super fast expansion, is one way to explain that.
And how do our theories, information density coherence energy, and the distributing force, deal with inflation? Do they offer any new insights?
Well, information density coherence energy, it suggests that inflation could have been triggered by a rapid phase transition in the early universe. Like, imagine the universe as this giant pot of water being heated at some point. It boils and turns to steam. And this transition could have been driven by an emergent field called the inflaton.
Okay, so a cosmic phase transition. Now, what about the distributing force theory?
It takes a slightly different approach. It says that the Big Bang might not have been this one-time explosive event. Instead, it could be more like a continuous process, with the universe constantly growing as its information density increases.
So no sudden bang, just a gradual unfolding of information driving the expansion of the universe.
Yeah, that's the general idea. And this leads to some really mind-bending possibilities. For example, if space-time is emergent, as both of these theories suggest, then the whole idea of what happened before the Big Bang might not even make sense.
Right. If space-time is created by information, then there might not have been a before in the way we usually think about it. Okay, my brain is officially fried. Let's move on to something slightly less existential, the matter-antimatter asymmetry. We know that matter and antimatter should have been created in equal amounts in the early universe, but somehow we ended up with way more matter. Why is that?
Yeah, that's a big one. The standard explanation is that there were tiny differences in how matter and antimatter interact, but it's still not totally clear.
So what do these new ideas have to say?
Well, the information density coherence energy theory suggests that the asymmetry could be due to the specific initial conditions of the universe. Or maybe there were subtle differences in how matter and antimatter interacted in that ultra-high energy environment of the very early universe.
So something about the initial setup or the extreme conditions tipped the scales. What about the distributing force?
It takes a more information-centric approach. It says that the asymmetry might be a consequence of how information itself propagates in an expanding universe. Maybe the very nature of information flow and the constraints imposed by coherence prevented perfect annihilation between matter and antimatter.
So the very act of information spreading through the universe could have created the matter-dominated world we see today. Okay, that's pretty cool. Now, no discussion of the universe would be complete without talking about dark matter and dark energy. We know they make up the vast majority of the universe's mass and energy, but we have no clue what they are.
Yeah, those are two of the biggest mysteries in cosmology. We see their effects, dark matter holding galaxies together, dark energy causing the universe's expansion to accelerate, but we can't see them directly.
So what light do these new theories shed on this dark side of the universe?
Well, one suggestion is that dark matter might not be a new type of particle, but an emergent gravitational effect. Like, maybe it's a consequence of the way gravity works in this information coherence framework. Or maybe it's somehow connected to hidden dimensions.
Okay, so it's not new stuff, but a different way of looking at gravity. What about dark energy?
Some connect it to the cosmological constant, that weird energy that seems to be inherent in space itself. And they suggest that maybe the cosmological constant is linked to the quantum information content of the universe.
So the more information the universe has, the more energy in space itself.
Yeah, something like that. Now, the distributing force theory, it goes in a completely different direction. It says that dark matter isn't a new substance at all, but a coherence effect that happens in galaxies.
Coherence effect? What does that even mean?
Imagine the core of a galaxy where you have tons of stars and stuff packed together. It has really high information density, right? Well, this theory says that high information density leads to these super strong coherence fields that can mimic the effects of dark matter.
So it's not actual matter, but this coherence thing making it seem like there's more gravity than we'd expect.
Exactly. And this theory even predicts that we should be able to detect specific coherence gradients around galaxies, which would be pretty amazing if we could actually observe that.
And what about dark energy? What does it say about the expansion of the universe speeding up?
It says that dark energy is just a consequence of the universe's increasing information density. Like, as the universe evolves, it becomes more complex, more information-rich. And this increase in information density could be what's driving the acceleration.
Okay, so it's not some mysterious force pushing the universe apart, but just the universe getting smarter, so to speak.
My mind is officially blown. Now, one more biggie, the idea of extra dimensions. Some theories, like string theory, suggest that our universe might have more than just the 3 dimensions of space and one of time that we experience.
Right, like those extra dimensions might be curled up so tiny that we can't perceive them directly.
So what do these new theories have to say about extra dimensions? Well, if space-time itself is emergent, as both of these theories suggest, then those extra dimensions might not be physical in the way we usually imagine them. They could be more like mathematical constructs or like effective degrees of freedom in the information structure of the universe. It's like saying that the way information is organized can create the illusion of extra dimensions, even though they might not exist as separate physical spaces.
Okay, so it's not that we're living in a 10-dimensional space. It's more like the math of information makes it seem that way.
Yeah, something like that.
Yeah.
And this way of thinking suggests that the shape of our universe, the way it's all connected, could be determined by constraints within this underlying information network.
So we've gone from the biggest scales of the universe back down to the very nature of reality itself. And through it all, we're seeing this theme of information and coherence emerging as potential keys to understanding everything. It's a lot to take in, but it's also incredibly exciting. Now, for the rest of this deep dive, I thought we could focus on some of the more specific mysteries that these theories try to solve, starting with a really perplexing one, the hierarchy problem.
Right, the hierarchy problem. It's this puzzle about why gravity is so incredibly weak compared to the other forces. Like, it's mind-bogglingly weak. Think about it. You can pick up a paperclip with a tiny magnet, overcoming the gravitational pull of the entire Earth.
It's like gravity just doesn't get invited to the party with the other forces. So how does this Information Density Coherence Energy theory explain that weakness?
It basically says that gravity isn't a fundamental force in the same way as the others. Instead, it's this emergent effect, a consequence of the coherence within the universe's energy density structures. It's like saying that gravity is the collective phenomenon, a result of the information structure of the universe as a whole, rather than something carried by a single particle like the other forces.
So it's not that gravity is weak. It's more like it's spread out across the entire universe, so we only feel its effects on a large scale.
Yeah, that's one way to think about it. And this view even suggests that the Planck scale, the energy scale where gravity is thought to become as strong as the other forces, might actually emerge naturally from the way these coherence layers interact and stabilize themselves.
Okay, so it's all about the structure and organization of information, even at the most fundamental level. What about magnetic monopoles? We know that magnets always have a north and a south pole, but why haven't we ever found a magnetic monopole, a magnet with just one pole?
That's another one of those puzzles that has bugged physicists for a long time. But the theory we're looking at today, it actually has a pretty elegant explanation. It says that the very way magnetism emerges within this framework prevents isolated monopoles from existing.
So it's like the rules of the game just don't allow for it.
Exactly. The way these infra-energy fields interact, they always create these dipole configurations, north and south poles always come in pairs. But the theory does suggest that under super extreme conditions, like near quantum critical states in certain materials or in incredibly strong magnetic fields, we might see something that behaves like a monopole, even though it wouldn't be a fundamental particle.
So it's not that monopoles are impossible, but they're just not allowed in our everyday low coherence world. Okay, let's talk about a more recent mystery, the neutron lifetime puzzle. Experiments have been giving slightly different results for how long a neutron lives before it decays, which is kind of unsettling for something that should be a fundamental property of the particle.
Yeah, that's been a head-scratcher for sure. And the theory we're discussing offers a really interesting take on this. It says that the neutron's lifetime isn't actually a fixed constant, but it can be subtly affected by the environment.
The environment, like what, the air pressure in the lab?
Well, it's a bit more complicated than that. It's about the local coherence energy density. Things like quantum fluctuations, virtual particles popping in and out of existence, even tiny exchanges of information with the background, all these things could subtly influence how quickly a neutron decays.
So even the supposedly empty space around the neutron isn't actually empty, and it can mess with the neutron's lifetime.
Exactly. And this theory even predicts that if we could create a perfectly isolated environment with ultra-low information density, a neutron would live longer because there wouldn't be these subtle influences messing with it.
So the neutron's lifetime is kind of like a measure of the noise in the quantum vacuum. That's a really cool way to think about it. Now, what about supersymmetry, or SUI's Y? This is an idea that's been around for a while, suggesting that every known particle has a heavier partner particle. But so far, none of these superpartners have been found, which is starting to make some physicists nervous.
Yeah, COSY was a really popular idea, but the lack of experimental evidence is making some people question it. But the theory we're talking about, it offers a different perspective. It suggests that the properties of particles, like their mass and charge, might not come from some fundamental symmetry like CSY, but rather from the way they interact within this coherence energy framework.
So instead of looking for these superpartner particles, maybe we should be looking for more subtle signs of this underlying coherence energy structure.
Exactly. Those missing superpartners might not be missing in the traditional sense of being too heavy to detect. They could be manifesting in completely different ways, as tiny distortions or excitations in the energy states of the particles we already know.
So it's a whole new way of thinking about particle physics. What about color confinement? This is the idea that quarks, the particles that make up protons and neutrons, can never be observed in isolation. They're always bound together within these composite particles.
Right. It's like quarks are super glued together. You can't just pull one out and look at it on its own.
So how does this information density coherence energy theory explain that?
It says that quarks are inherently part of these information coherence structures. They only exist as stable combinations within hadrons because those configurations are the most energetically favorable and informationally coherent states they can be in.
So an isolated quark just wouldn't make sense in terms of information and energy.
Right. But it doesn't rule out the possibility of exotic multi-quark states, or maybe even fleeting moments, where quarks are freed under extreme conditions, like in the early universe or in high-energy particle collisions.
Okay, so there's still room for some really weird stuff. Now, what about the QCD vacuum, the so-called empty space in the context of the strong force? Quantum field theory says it's actually teeming with virtual particles popping in and out of existence, which seems pretty far from empty.
Yeah, it's definitely not the kind of vacuum you'd find in your house. But the theory we're exploring, it describes the QCD vacuum as something really interesting. It says it's not empty, but rather a self-organized coherence structure.
So it's more like a structured background, a kind of fabric woven from information and energy, rather than just nothingness.
Exactly. And this means that the vacuum itself can have an influence on particles and forces. It's not just a passive backdrop, but an active participant in the quantum world.
Okay, that's a pretty mind-blowing concept. Now let's revisit something we touched on earlier, but this time from the particle physics perspective. Why are there three generations of matter particles, like the electron, muon, and tau, and their corresponding quarks? And why is there this matter-antimatter asymmetry where there's so much more matter than antimatter in the universe?
Those are some really fundamental questions. The standard model of particle physics doesn't really explain why there are three generations. It just kind of accepts it as a fact. And the matter-antimatter asymmetry is a whole other mystery. But these new ideas, they offer some potential insights.
So what are they?
Well, the information density coherence energy theory suggests that the three generations of matter might correspond to different levels of stability within the universe's coherence energy structure. The heavier particles, like muons and teis, are like higher energy excited states, and they eventually decay into the more stable, lower energy states like electrons.
So it's like a hierarchy of stability determined by information and energy.
Yeah, something like that. And as for the matter-antimatter asymmetry, this theory says it might be a consequence of how information propagates in an expanding universe. Maybe the constraints imposed by coherence prevented matter and antimatter from completely annihilating each other, leading to the matter-dominated universe we see today.
So it's like information itself tilted the scales in favor of matter. That's pretty amazing. What about neutrinos? We know there are these incredibly light, weakly interacting particles that are super hard to detect. Why are they so different from other particles?
The theory we're discussing has a really interesting explanation for that. It suggests that neutrinos are actually high-coherence information carriers. Because they have such high coherence, they don't interact much with space-time or other matter, which explains why they're so light and why they can pass through almost anything.
So it's like they're surfing on this wave of coherence, barely interacting with the rest of the universe. Now, we've talked a lot about cosmology and particle physics, but these theories have implications for other areas of physics as well. For example, there's the proton radius puzzle.
Oh, yeah, that one. It's weird, right? It seems like the proton has a slightly different size depending on whether you measure it using muons or electrons.
Exactly. So what's going on there?
Well, this theory suggests that the act of measurement itself, the particle used to probe the proton, actually interacts with the proton's internal coherence state differently.
So the measuring tool is actually affecting what we're trying to measure.
Yeah. Muons are much heavier than electrons, so they interact more strongly with the proton, and that could be why they give a slightly different size measurement. The theory even suggests that the proton size might vary subtly depending on the local coherence conditions in the experiment.
So even something as seemingly fundamental as the size of a proton might depend on the information environment it's in. What about quark combinations? We know that quarks bind together to form particles like protons and neutrons, but are there any rules about which combinations are allowed? And what about these hypothetical particles called glue balls, which would be made entirely of gluons?
The theory has some pretty specific answers to those questions. It says that the only allowed quark combinations are those that result in stable coherence configurations. So it's not just about random quarks sticking together. It's about finding those combinations that create a harmonious balance of information and energy.
So it's like quarks are playing a cosmic Lego game, and only certain combinations click together.
Exactly. And as for glue balls, the theory predicts that they should exist as pure coherence energy states. They'd be like these bundles of pure gluonic energy held together by the strong force, but without any quarks.
So it's like finding a Lego structure made entirely of the connecting pieces without any of the colorful blocks.
Yeah, that's a good analogy. Now let's talk about something a bit more down to earth, at least in terms of scale, atomic structure and the periodic table of elements. We have a pretty good understanding of how atoms work based on quantum mechanics, but does this new perspective offer any new insights?
Well, the distributing force theory has some really interesting things to say about atomic structure. It says that electron orbitals, the regions around the nucleus where electrons are likely to be found, aren't just random clouds of probability, but they're actually coherence zones.
Coherent zones. Like, what does that mean?
It means that electrons in those orbitals exist in specific, stable, coherent states. Each element has its own unique configuration of these coherence zones, which determines its chemical properties.
So it's not just about the number of protons and electrons, it's about how they're organized in terms of coherence. That's cool. What about radioactivity? Why do some atoms decay while others are stable?
The theory suggests that radioactive decay happens when an atom's configuration of protons and neutrons can't maintain a stable level of coherence. It's like the atom is trying to reach a more harmonious state, and sometimes that involves kicking out particles or energy.
So it's a quest for coherence, even at the atomic level.
Exactly. And this perspective even hints at the possibility of finding new, stable elements that we haven't discovered yet. Elements where the information density and coherence are just right to create a superstable configuration.
That'd be pretty amazing. Now, let's tackle the big question of force unification. Physicists have been trying for decades to find a single theory that explains all four fundamental forces: gravity, electromagnetism, the strong force, and the weak force.
Yeah, that's the ultimate goal, to show that all these forces are just different aspects of the same underlying reality. So how does the distributing force theory approach this?
It suggests that the forces aren't truly separate at the most fundamental level. Instead, they're all manifestations of gradients in this underlying coherence field. Gravity, being the weakest, would be the most broadly distributed gradient. The strong and weak forces would be more localized, higher energy gradients, and even the strength of electromagnetism could vary depending on the local coherence conditions.
So it's all about the shape and intensity of this coherence field. And the forces we see are just ripples or wrinkles in that field.
Yeah, that's a good way to visualize it. And this theory even predicts that there might be other intermediate forces that we haven't discovered yet, bridging the gaps between the known forces.
Okay, so we might be missing some pieces of the force puzzle. What about light and electromagnetism? The speed of light in a vacuum is supposed to be constant, one of the cornerstones of physics. But does this theory have anything new to say about that?
It does. It suggests that light isn't just an electromagnetic wave, it's also a coherence wave, propagating through the universe's underlying coherence field. It's like, imagine a ripple traveling across a pond. The ripple isn't a thing in itself, it's a disturbance in the water.
So light is a disturbance in this coherence field.
Exactly. And this has a really interesting consequence. It suggests that the speed of light might not be absolutely constant under all conditions.
Wait, hold on. You're saying the speed of light might not be constant. Isn't that like physics heresy?
It sounds crazy, right? But the theory suggests that in regions of super high coherence, the speed of light might vary very slightly.
So it's like the speed limit of the universe can be tweaked a bit in certain places. Okay, that's a lot to process. The distributing force theory also talks about some biological effects of light.
Yeah, it suggests that certain frequencies of light, like blue light, can actually disrupt our biological coherence. Our bodies are tuned to operate within a certain range of coherence, and when we're exposed to light outside that range, It can mess with our systems.
So it's not just about the energy of the light, but also about its coherence. That makes sense. Okay, let's revisit those cosmic giants, galaxies, and black holes. We know that galaxies rotate faster than they should based on the visible matter we can see, which is where the idea of dark matter comes in. But how does the distributing force theory explain those anomalous rotation curves?
It says that those fast rotation speeds aren't due to dark matter, but to the coherence fields created by the high information density in the cores of galaxies.
So it's like a coherence boost to gravity.
Exactly. These coherence fields strengthen the gravitational pull, making the stars orbit faster than we'd expect based on the visible matter alone. And this leads to a really cool prediction. We should be able to detect these coherence gradients around galaxies if we look closely enough.
Now, what about black holes? We've already talked about them as information processors, but what are they fundamentally, according to this theory?
It says that black holes are actually coherence condensates, regions where information density has reached this ultimate limit. They're not singularities, points of infinite density, but rather these incredibly dense, highly coherent structures.
And what does that mean for how we understand black holes?
It means that we might be able to see deviations from the predictions of Einstein's theory of general relativity very close to the event horizon, the point of no return around a black hole. Those deviations would be a sign that black holes are more complex than we thought, that they're governed by these principles of coherence.
Okay, so black holes are even weirder than we imagined. We've also talked about dark energy, that mysterious something causing the universe to expand faster and faster. What does the distributing force theory have to say about that?
It says that dark energy isn't a separate force or entity, but it's a direct consequence of the universe's increasing information density. As the universe evolves, it generates more information, becoming more complex. And that increasing information density, according to this theory, is what's driving the acceleration.
So the universe is like a giant brain getting smarter and smarter, and that's causing it to expand faster.
That's a pretty cool way to put it.
Okay, we've covered a lot of ground.
Yeah.
From the tiniest particles to the entire universe. Can you sum up some of the key takeaways, the big ideas that these theories are suggesting?
Well, I think the biggest one is that everything, gravity, matter, all the forces, might be different manifestations of underlying coherence energy information structures. This means that our current theories, like the standard model of particle physics, are,